Hi class, we are on now chapter 15.5 and we're going to be looking at reaction rates. So factors that affect a reaction rate. Rate often depends on the concentration of one or more of the reactant molecules. The rate law is an equation relating to the concentration of reactions to the rate when the reverse reaction is negligible. Basically, what that means is that when the reverse reaction is so slow that we can just count it as it's not even going in reverse reaction. So rate laws include a proportionality constant called a rate constant, K, which is determined experimentally, and a term for the concentration of each reactant raised to the power of its order n, which is also determined experimentally. So the general rate law is something that we've already seen from the previous section. So this is the general rate law. Remember, the coefficients or whatever is, if it's a coefficient of 2, for instance, for reactant, we now have it at the bottom with the change in time, and we have to have the negative, and that is going to give us the rate constant, which is a proportionality constant, so I'm not wrong. The concentration of A, and N as its order. So it's the power of its order by N, and we're going to take a look at that in this section. So again, the rate of a reaction is directly proportional to the concentration of each reaction raised to a power. So if we look at a reaction, just a generic reaction of A that then produces products, the rate law would have to be the rate equals K, which again is the rate constant, and the concentration of A to the power of N. N is the order. It's usually an integer that determines the rate dependence on the reactant concentration, and K again is the rate constant. Okay, so reaction order. The exponent on each reactant in the rate law is called the order with respect to that reactant. So, and then when we have a couple of them, or right now we have 2, which is a couple, what happens is that you add the sum of the exponents on the reactants is called the order of the reaction. So you would add the orders up, and then it would take you, so the reactant itself will have an order, but when you do the total, there will be another order overall, usually, unless one is like 0. Then it's going to stay in the same order. But I don't want to even start with that. Let's just get started before I start saying things that are going to confuse you worse. So in this rate law, we have the rate, we have the rate constant, we have the concentration of nitrogen oxide to the, the reaction is in the second order with respect to the concentration of nitrogen oxide or nitrogen monoxide. First order with respect to oxygen, and third order overall, because there's a 1 here that by default we don't say. So this is second order with respect to this reactant, first order with respect to this reactant, and 2 plus 1 is third order overall. Now you can't get that information here. I know that it just happens to match up here with the coefficients, but in other reactions it does not. So you can't assume that the coefficients are actually going to be the order. So reaction order N. Common values of N are 0, 1, and 2. You can even get a 1/2. Although negative and fraction values are possible. So that would be a 1/2. So if you get a 1/2, it is possible to have a 1/2. We just tend to focus more on the 0, the whole numbers. When N is 0, the reaction is 0 order with respect to A. When N equals 1, the reaction order is first order with respect to A. And when N equals 2, the reaction order is second order with respect to A. And we're going to break these down. When a reaction has multiple reactants, each reactant has its own order, and the overall order is the sum of those. So that was a perfect example of here, where each reactant has its own order, but then we sum all of the reactants up based on their order. Okay, so a general rate law. So we've taken a look at this. Let's say that we have reactants of A and B. So we determine the rate, and we want to determine N, and we actually want to determine M. And we have to do all of this, the K, N, and M, experimentally. So if N and M are both equal to 1, then the reaction order is first order with respect to each reactant and second order overall. So if so we can say the first order the concentration of A is first order with respect to that reactant, and the concentration of B is first order with respect to the B concentration, and summing them together is a second order overall. So when a reaction has multiple reactants, each reactant has its own order again, and then an overall reaction order for those reactants that are in the general rate law here. Okay, so if a reaction is zero order, the rate of the reaction is always the same. This means it stays constant no matter, oh, look at my arrow changed. This arrow is supposed to be here. So just imagine it visually here. Okay, so a reaction of zero order means it stays constant. The rate is the numerical value you have is not going to change no matter what you do to it. So you can double the concentration of A, you can decrease the concentration of A, and it's going to stay constant. The concentration of A has no effect on that reaction rate. It's just going to keep going on its own. If a reaction is first order, the rate is directly proportional to the reaction concentration. Now the key words there are directly proportional. That means that if the concentration of the reactant concentration goes up, the rate will go up. If the concentration reaction goes down, then the rate will also go down. So whatever happens to one will happen to the other equally. So in first order reactions, n equals 1. The rate law is simply, so if we had this rate law and we put a 1 here, then you don't no longer see the 1 here because we usually don't put 1s on anything. It's there as a default, but we don't put it. Doubling concentration of A will double the rate of reaction. So this is exactly what I said. Or if you decrease it by half, you're also going to decrease the initial rate. So these are initial rates that we're looking at. Not the whole rate throughout the concentration, but the initial rate. If a reaction is second order, the rate is directly proportional to the square of the reactant concentration. Now this one's a little harder for people to understand, but what's it saying is the rate is directly proportional to the square of the reactant concentration. I just repeated myself for no reason. Doubling the concentration of A will quadruple the rate of the reaction. So basically, you have to look for two things if you're dealing with the second order. The concentration of A will double, but the rate of the reaction will quadruple. So by 4 times it will increase. In a second order reaction with a single reactant, then N is equals 2, and we would plug N 2 where the N would be. And that's where it means that we can double it and then the quadruple. When the concentration of A is doubled, the rate of the reaction increases by a factor of power of 2, so this is equal to 4. So that's why you would see the rate actually quadruple. If it doubles, then you're most likely dealing with a first order reaction. If it's doubling on the concentration, you are dealing with a first order reaction where the concentration doubles and the rate doubles. But if you're dealing with a second order, the rate doubles, but the concentration doubles, but the rate quadruples. And I have some examples. When the concentration drops to 1/2 of its initial concentration, the reaction rate is 1/4 of the initial. So it's always by 1/4 or it multiplied by 4, and when the other one is either doubled or 1/2. For a particular reaction in which A produces products, a doubling of the concentration of A causes the reaction to double. So this is directly proportional. This means that if one is affected in one way and the other one, such as the rate, is affected in the same exact way, then this is a first order reaction. The rate is directly proportional to the reactant concentration. So doubling A, the concentration will also double the rate. The rate of reaction. So determining the order of a reaction, your book shows you 2 ways, and we of course are going to take the easier way to do this. The rate law must be determined experimentally. So we're going to have you get a list of through experiments, you chart or put a table together of initial rates of everything that you've done for these reactants, and we can pull that data and we can figure out which is the order for those reactants and then the total. So we use the method of initial rates, where data from different experiments with different starting concentrations of reactants and the corresponding initial rates are given. We can determine how the rate is impacted by a change in a single reactant in 2 different experiments. So basically, we hold one constant and we change the concentration of the other, and then we can see what happens to the rate by changing that concentration. And then we do it for the other reactant. We keep the one reactant constant, and we double the other one, and we see what happens to the rate. That's all that's basically saying. So we measure the reaction's initial rate at different concentrations of the reactant, and we keeping all other conditions unchanged. That's the key thing. Everything else has to stay unchanged. So we know that by controlling this, if the rate goes up, it's because of that reactant. So we write a general law, rate law. Again, this is going to come up over and over again. And then we can compare the changes in the rate to the changes in the concentration to determine N. And now we can set it up. So we're going to do a ratio of one rate, which is the lower rate as time goes on. And then the second rate is further in. So this is sort of final minus initial, but we're not really looking at final and initial conditions. We're looking at one that's earlier than the other. And then we match the corresponding concentration with those values. So we set this up as a ratio. And then your book actually breaks down these steps, how to do the log. I did not put that here, but if you need help to go over that, we can definitely go over it on one of the days that we don't have a lab. It's really easy, the steps. Just make sure you're comfortable with using log on your calculator. It's not really difficult at all. So here is a perfect example. We have experiments, 3 experiments were done, and we have the concentration of A, and you can see it looks like we doubled it and we doubled it again. And then we have an initial rate of the reaction. Okay, so we're going to compare experiments 1 and 2, and the whole thing is we're trying to find the order of this. So we set this up, rate 1. Oh, look at what they did here. They switched it, and they shouldn't have, and I don't know why they did that. Yeah, I don't know why they did that. So this should be 2, and this should be 1. So actually what it is these numbers are transposed. I don't know why I catch these things until I'm recording. This is 2, this is 1. It should actually look like this, because if you notice, these are experiments 1 and 2. So the 2 should be here, and it is. The rate of it is on top. Experiment 1 is on the bottom. And when we divide one into the other, the rate is 2.0. Now this, your book shows you how to do this all in one step, but this is showing you, I think I mentioned previously, I used some slides from another course that I taught, because some of the slides explain and have more examples than what's been given with your book. So this does it in a little different way, and it skips doing the log steps that you have to do. So on A, see, the 2 is correct, the 1 is correct on this one. And so we take the concentration of experiment 2 over concentration of experiment 1, and it gives us a 2. So then when basically you divide these using the log and so forth, because you're trying to determine N, this is 1. So when the concentration of A doubles, the rate also doubles. So N equals 1. And the rate, so we have the rate and the rate constant. This is a first order reaction in respect to the concentration of A. You can also notice, if you looked at just these numbers, this doubles, this also doubles. And that's kind of a visual to also help you see. And if you have any doubts, you definitely should do this. But after a while, you can start looking at this and you can see a quadruple and you can see a double when these things happen. Okay, so we rearrange. So what if you wanted the rate law? So the rate law, here's the formula. We can take the information from this, we can move this around and determine what K is. So we can take this information and we can take experiment 1, plug that in for the initial rate, and then we have the concentration of K, of experiment 1, and that's going to give us our rate. So we can also solve for the rate once we have this information. So using, if it's asking for the rate law for the value of K, that's what K is. This is now K for the concentration of A. Okay, so what happens if you have multiple reactants? So changing each reactant will affect the overall rate of the reaction. So by changing the initial concentration of one at a time, the effect of each reactant's concentration on the rate can be determined. So basically it's just what I said. We hold the other reactants constant, so we don't change the concentration, but we pick one and we increase that concentration, and then we check the rates and to see if there's any change, and if there is, what is that change, so we can determine what the order is. So in examining results, we compare differences in rate for the reactions. I'm just repeating, differing only concentration of one reactant. So where M is the reaction order with respect to A, N is the reaction order with respect to B. And we're going to solve, further on, we're going to solve a reaction solving M and N. Okay, so we determine the order of each reactant from experimental data. So in this case, we didn't do the experiments, but they're going to give us tables, and we're going to take the information. So the resulting rate law would have the following form. So if it's asking for the rate law, you have the rate, which is equal to the rate constant, and then we have M. I always mess this up the way I say it. M is the reaction order with respect to A, and N is the reaction order with respect to B. So if I mess that up, I don't mean to. And then there is an overall order where we add M and N together. Okay, so let's take a look at this. Again, I didn't break down each step with the log. Your book really does a great job of breaking that down, but if we need help, we can always go over that. Okay, so we want to determine N on this. So we have our rate law, and we set it up, and N is in respect, in this case, N is in respect to the concentration of A. So we have the concentration of A, we have the concentration of B, and we have the initial rate for these experiments of the concentration of A and the concentration of B. So we want to compare experiments 1 and 2, where the concentration of A changes, but if you notice, B stays constant. So this is a perfect example of that. And so it shows the rate quadruples when A doubles. So A doubles, so we should instantly look for a couple things. We should look, did the rate double or did it quadruple? And in this case, it quadrupled. So we're actually looking for a second order with respect to A. So this is where you can kind of, if you can start seeing this stuff, you don't have to actually work out each problem, but it's not always going to be this easy. So comparing experiments 2 and 3, where we can see that A, the concentration of A is kept constant, but so when we keep this constant, we increase the concentration of B, but what we notice is that the initial rate didn't change. So when the initial rate didn't change, this means that M is 0 order. So that's one of the, remember that 0 order is the rate stays constant no matter what. It's not going to be affected by how we change the concentration of that reactant. It's just going to keep going. So this is a perfect example of that. So M is 0. The reaction is 0 order with respect to B. So if we look at the rate law equation, we have rate, we have K as the rate constant. We have the reaction is second order with respect to A, and then this one is the reaction is 0 order with respect to B. So if we show this, then the rate is equal to actually just the concentration of A with the with the second order, because this one's not affecting this reaction at all. It's everything, any changes that are going to happen, it's going to be with the concentration of A. Okay, so now let's take a look at another problem. I highlighted the experiments that this is asking for. So compare experiments 1 and 2, where the concentration of A changes and B is constant. So we're just trying to figure out the order of these reactions again. So I didn't specifically state that on here, but that's what you're doing. So if we look here, we're looking at we have 8.6 times 10 to the negative 3. So the rate 2 over rate 1. And then we have this in if you didn't know which one you were looking at, when we're doing this, look for the constant. So this is the concentration of B. We're not looking for the concentration of B. We're looking for the concentration of A. So even if this didn't say anything here, look at the values. It's for A. So when we plug this in, we can, again, the log, breaking this down and solving for N is not done here, but you got to use the log. And what you're going to end up getting is this is N equals 2. So this is a second order, and if you looked at it, you could probably see this doubled, this reaction rate quadrupled, and that's another way to look at it. Okay, so this reaction is second order with respect to A, and this is how you would plug this in. We have the rate equals the rate law equals the rate constant, and this is second order with respect to A. But what about B? We don't know what B is, so let's finish and get B. So now I've highlighted experiment 2 and 3, where concentration of A is kept constant, but we have increased the concentration of B, so we can see what's actually happening here. And when we increase the concentration of B, we can see that so rate 3 goes over rate 2, and this ends up basically through all the calculations, which are not here. We can see that this is a first order reaction M is a first order reaction with respect to the concentration of B. So when we plug this all in, we have a rate that looks like this. This is a 1, actually a 1 here. So rate is equal to the rate constant with the second order with respect to the concentration of A, and first order with respect to the concentration of B. And if you had to plug these, add them all, it is a third overall, a third order overall. Now, what about the constant? What if we wanted to solve for K, the rate constant? We simply take this equation and isolate K, plug in our values, and now that we know the order to these, that actually will, if you don't know the orders, this isn't going to be correct, but we have the correct orders, and we can solve for our rate in respect to second order in respect to the concentration of A, and first order in the concentration of B. Okay, so this is just an overall, so you can see so the units also change, and the order of the units and how they change. So this is molar over seconds, this is 1 over seconds, this is 1 over molar per second. So these, you can see that these are changing based on the order. Okay, so let's do a problem. Determine the reaction order and the value of the rate constant for the decomposition of nitrogen oxide gas from the following data collected at 300 degrees Celsius. So we're looking at the concentration of nitrogen dioxide. That's all this is. If you notice, that's all that we have here to work with. That's what we're going to look at. And we need to know, this is asking for the reaction order and the value of the rate constant. And remember, once we get the reaction order, we can solve for K. So that's not too bad. Okay, so we're going to write a general rate law. Make sure you're comfortable understanding what the general rate law is, because that's how you move things around in order to solve. All right, we're going to look at experiments 2 and 3. Why we're going to look at those? Because these double. These are double. So this is the one that we're interested in. We don't want to get ones that are complicated. We want one that's double. So doubling the concentration of nitrogen dioxide causes the rate to quadruple. So this is a second order. So solving for this is a second order. So 2 is the reaction order with respect, a second order with respect to nitrogen dioxide. I know I slaughter that every time I say it. Okay, so now that we solved for the reaction order, we know it's 2, we plug that in, we can now solve for K. And by solving for K, we set this up, we take the information from experiment 2, we can take that, and that is going to give us our rate constant for K. All right, so now we have solved A and we've solved B, but let's change the concentrations to something that's not on the table. Now we have the rate constant, so we have certain information here, but I think in this problem they actually gives you a different rate constant because those are based on those concentrations. So let's take a look. So, oh no, this is another one I guess I did. Okay, so determine the rate law for the reaction. So rate quadruples when nitrogen oxide doubles. So if we take a look here. Okay, so let's look at this problem. I thought it was related to the other one. It's late. Now, if we look at, let's look at the writing. There's a mistake on here, and I hope you guys can catch it if you look close enough. When we look at the concentration of nitrogen monoxide, when we look at this, we see that the the concentration has doubled, and this is quadrupled. So if you ever get confused, you can also divide this into this, and if it gives you 4 or close to 4, 3.89, 3.9, you're quadrupling the rate. So this quadruples. This means that this must be a second order. Now, if you look here, though, it is true, it is correct, but the way they worded it, it's wrong. If you notice, we start out with this concentration and it decreases in concentration, and the rate also decreases. So that also means that, remember when we were talking about first order, if you double a concentration, the rate also doubles, and if you decrease the concentration, the rate also decreases. So they're saying this doubles when they should be stating that this decreases, and so the rate is also decreasing, but it's still a first order reaction with respect to oxygen. So the rate of both these is second order. It's a second order with respect to the reactant of NO, and it's a first order with respect to oxygen. Okay, so now that we know the correct order numbers for these reactants, we can solve for K. So we plug everything in, we make sure that we have our reaction order number with the correct reactant, and then we solve for K, which it gives us that value right here. Okay, so now this is giving us different concentrations that are not listed here, which means that we also don't even have the initial rate, but we solved for the initial rate on the previous page. So we have the initial rate, yeah, we have the initial rate, and we're going to use the initial rate and plug in these different concentrations that are not listed here, and we can figure out what the rate is for this reaction, and which we do. We plug it in with the correct or a reaction order number, and it'll give us our rate value. So here's a review. Reaction rates can be measured as average or instantaneous rates. Instantaneous rates, this is from the previous section, are measured close to the start of the reaction, are called initial rates. Rate laws are experimentally determined mathematical relationships between the reaction rate and the concentration of the reactants. For reaction with a single reactant, K is the rate constant, and N is the order with respect to A, as well as the overall reaction order. For reaction with multiple reactants, A and B, K is the rate constant when N is the order with respect to A, M is the order with respect to B, and the order of the overall reaction is N plus B, the sum of the orders with respect to each reactant. We deal with common reaction orders of 0, 1, and 2, but you can get halves, 1/2, and so forth. Right now it's easier to just stick with whole numbers. Units of the rate depend upon the overall reaction order. Of course it does, because we need those values when we plug into the equation. And that's it.